Wingardium Leviosa. Wingardium Leviosa. Wingardium Leviosa. Wingardium Leviosa. Wingardium Leviosa. So much for magic. But what is magic anyway? Isn't it just simply science that hasn't been explained yet? Well, if I want this to fly or levitate, I'm going to need to do some scientific explanation. What we're going to talk about today is static charges, or charges of electricity. And how those charges behave with each other is going to actually tell us a lot about how solutions, liquids, operate. To start off with, let's just talk about static charges. Did you ever take a balloon, rub it against your head, try to stick it on the wall? If you've done that, then what you've probably done is realize that you've taken a piece of rubber, rubbed it against hair, and created a negatively charged object. I'm going to do that right now with a different type of wand. This one right here. This is a wand that has nothing more than cardboard, and inside here is a long rubber band. If I push the button, the rubber band rubs against something that's a lot like your hair and creates a static charge of negative electricity on this wand. So let's try that. And we can see my little object now can float in the air, and I can move it magically with my wand. So the wand is negative, the orb is negative, and negative charges repel. Opposites attract, like charges repel. And if you look at the orb itself, every piece of that orb is getting as far apart from the other piece as possible. Exactly the same way electrons try to get as far apart as possible around the atom that they're associated with. Now, water is a polar molecule. That means it has a positive side and a negative side. Well, if it has a positive side and a negative side, then could we attract water as if it was a magnet with something that was charged? I could use my magic wand, but you probably don't have a magic wand at home. So I'm going to change it for something that you probably do have at home, which is just a piece of plastic. Now you want a nice hard plastic. And if you've got, say, a genuine fur hat, you can rub, just like rubbing a balloon on your head, or my other wand that had the rubber band inside. What I'm doing is I'm getting electrons to come off this fur onto the plastic spatula. And as long as the spatula is dry, it'll build up a nice negative charge. Now that charge should be enough that when I bring it to a small stream of water, now you want a very narrow stream of water, so let's see, whoa, and I can bend that water right to the rod. Can I do it the other way? Yes, because the water is polar and the rod is attracting the positive end of those water molecules.
The static charges that are making that water bend also lead to some other magical qualities. 3 questions I have for you. 3 questions about water that you've seen, but maybe never really thought about. Question 1, why does ice float? Things are solid, they're more dense, and you would think that if they're denser, they'd be heavier and ice should sink. And how can some bugs walk on water, or even some small animals for that matter? And why don't oil and water mix? And here I have some photos of, this is a Chinese water lizard running on top of the water, and of course the water strider on the right. We used to call these guys Jesus bugs because they walk on the water. How come they don't sink? How come they don't fall in? Now, the partial charges have to do with electrostatic charges. That's the charges we just demonstrated. Rubbing a balloon causes it to stick to the wall because the negative electrostatic charge is built up on the balloon, and they're attracted to the slightly positive charge of the wall. And any charge that's just sitting there, not moving like in a wire or an electric current, is called a static charge, or in this case, an electrostatic charge. So a positive charge is not moving, it's existing on a substance like the spatula. In chemistry, we write these charges using a Greek delta. That symbol there is actually like a small d in Greek, and that stands for partial charge. It's not as strong as a proton or an electron, which would be a full positive or negative charge. And we've seen this before. This is a partial positive charge and a partial negative charge. And we use that when we draw molecules and show which side has what charge. So if we consider a water molecule, we can see that this big ball here would be the oxygen. These two smaller ones would be the hydrogens. There's a lone pair of electrons sitting out here on the oxygen. So we draw a delta minus, meaning negative charge exists. And then over here we have the two hydrogens. Since a hydrogen is nothing more than a proton, its electrons involved in this bond. So this area is more positive. So you have a positive side and a negative side. And that gives us something we call a dipole. And that gives the water molecule its polar nature. Polar molecules are molecules that are attracted to a charge because they have partial charges on them. Non-polar molecules, on the other hand, don't have a positive side and a negative side, so molecules that are not attracted to a charge are called non-polar molecules.
So let's see. Whoa, and I can bend that water.
If we took a look at what was happening, this is our stream of water coming down, and this would be our charged wand or our spatula. Inside the spatula, I've charged up with the hat, and now we've got a lot more electrons sitting on the surface of that wand. That's creating a negative static charge. It's attracting all the positive sides of these water molecules. So they all orient themselves this way. This negative side then attracts the positive of the next set of water molecules, and so on and so on, and the entire stream bends toward the wand. The individual molecules in polar liquids will respond when another charged substance comes near it. So in hydrogen bonding, what you see is the positive side of one is attracted to the negative side of another. The negative side of this one is attracted to the positive of this side. The positive of this is attracted to the negative of that. And we have these molecules wanting to stick together. That hydrogen bonding is pulling them together. Not as strong as a full bond, but there's an attractive force there. These are called intermolecular forces, forces that of attraction that occur between molecules. Now, all molecules do interact with each other, but the attractions between polar molecules are stronger than the ones between the nonpolar molecules. So let's go back to our questions. Why does ice float? Well, if substances get denser as they cool, shouldn't they sink? Here we have a whole bunch of water molecules attracted to each other by their hydrogen bonding. They're just all sliding around each other because it's a liquid. But what happens when this cools into a solid? The atoms are forced to line up because they stop moving and sliding around. As they line up, negative to positive, positive to negative, negative to positive, they create these spaces in between them. That is their structure. And these spaces are what cause the ice to actually expand. So it's less dense than water. And if it's less dense than water, it floats. So when ice freezes, the positive and negative charges pull the molecules into formation, causing the ice to expand. Second question. How can some animals walk on the water? A water molecule is pulled equally in all directions by the other water molecules around it. So here's my one water molecule, and here's other water molecules around it. They're all going to pull on each other, and they're all going to have this force of attraction, and all those forces will balance out. All except molecules on the surface has a molecule below it pulling, one to the left, one to the right, but it doesn't have any molecule above it pulling on it. So what happens? These top molecules get pulled down. As they get pulled down, that top surface actually gets thicker. And this top layer of water is called the meniscus. And when you look in a graduated cylinder or a test tube, you'll see that extra thick layer of water on top. That's the meniscus. Since this is actually denser than water, if something is light enough not to break through that, this dense layer will support that object.
Have you ever seen how you can float a rubber band on a bowl of water? Or even a paper clip? How can I float paper clips on water when a paper clip itself is heavier than water? So if I just drop it in, it just goes right to the bottom. I can float these guys on top because of something called surface tension. That's that meniscus of extra thick water on top. If I touch this and push this right below the surface, boop, falls right to the bottom because the water is less dense than the metal. But the meniscus is more dense. That's what allows those bugs and even that lizard to float on the water. Now let's try putting some pepper on the water. Can you guys see? Pepper just floats on top. The surface tension holds it up. But I can make pepper afraid of me. That's right. Pepper is terrified of me if I have some soap. If I put some soap on my finger, I will break the surface tension. The soap has a polar side and a non-polar side. When I put it in, boop, you can see, oh, that pepper doesn't want to be anywhere near me. It goes right to the side. And what would happen to our floating rubber band if we poured some soap in, mix it up a little bit, boop, the surface tension is broken by the soap molecules. So my rubber band and my paper clips just fall straight to the bottom. Here's another little thing you can try at home. If you take a cork and put it in some water, you'll see it'll like to go to the side of the container. It doesn't really want to sit in the middle, and that's because the water likes to stick to itself, but it also likes to stick to the side of the container. That's why the meniscus goes up at the ends. But if I want the water to go to the middle, well, I can do that by adding just a little more water to the bowl and filling it all the way up to the rim. If I can get it to the rim, the water will still stick to the container, but it will bubble up over the top. When that happens, the cork wanting to go to the highest point, because it likes to float, will, I don't want to get the port on the cork, go to the middle of the bowl, because that's the highest point of the water. If I can get that. Because the water bubbles up over.
So polar molecules have one side that's slightly positive and the other side slightly negative. Non-polar molecules do not. And intermolecular forces are the forces of attraction that occur between molecules. Hydrogen bonding is the strongest intermolecular force where the negative side of one molecule is attracted to the positive side of the other. Here's some behaviors of polar and nonpolar substances. Can you write these down in the column that they belong in? Can you divide up what are properties of polar and what are properties of nonpolar? Let's give us a minute to do this and start the video up again when you've got it down, and we'll check and see. Okay, so let's see. Are attracted to charged objects. Would that be polar or nonpolar? Well, that's a property of polar substances. Little attraction between molecules. Well, not much, but a little. That would be a nonpolar property. What would bead up on surfaces? Well, let's see. If we put water on something, the water would want to stick together. So bead up on surfaces, polar. Low surface tension. That would be nonpolar. I'm not attracted to charged objects. Well, that would be nonpolar. Which one would evaporate more quickly? Well, things that didn't have bonds holding them together. Nonpolar. Have molecules that stick together. Stickiness is a polar property. Evaporate slowly. If they stick together, they don't want to evaporate as quickly as if there's no force holding them together. High surface tension, the opposite of low surface tension, would be polar substances and spread easily and quickly on any surface. Well, that would be polar substances. And there you have it.